Let's say you want to load a web page, and your browser needs to fetch images, text, and data from a server. Historically, using HTTP/1.1, every one of those active requests needed its own dedicated physical connection to the server. If you wanted to ask the server for 6 different things at the exact same time, your browser had to open 6 separate network connections. Setting up each one costs time, memory, and processing power. You could try to reuse a single connection to save resources, but if you did, the second request had to sit idle in a queue. It couldn't take a single step forward until the first request finished completely. HTTP/2 changes this by collapsing all that simultaneous traffic into a single pathway. Instead of opening 6 different connections to have 6 different conversations, your browser and the server agree to use just one shared TCP connection for everything. To make this work, the data cannot be sent as raw, continuous text. Instead, HTTP2 chops every request and response into tiny, fixed-format envelopes. This shift allows a single connection to do the work of dozens. For the people running the servers, this means their hardware can support more users while using less memory. This diagram shows the fundamental unit of HTTP2. We call this envelope a frame. Every piece of data traveling through the pipe is protected inside one of these frames. The frame always starts with a strict 9-byte header, which tells the receiver exactly how long the payload is and what type of data is inside. Crucially, that header also includes a stream ID. This is a unique number stamped on every single frame, so the server knows exactly which conversation it belongs to. Client requests, for example, are always tagged with odd numbers, like 1, 3, or 5. Here's this in action. Frames from 3 distinct requests travel through the exact same pipe, mixed together. Because data is chopped into frames, large transfers don't block smaller ones. Watch Stream 3 complete a fast round trip seamlessly, right inside Stream 1's massive file transfer. When this mixed-up stream of frames reaches the other end, the receiver reads those stream ID numbers. It uses them to sort the envelopes and perfectly reconstruct each distinct conversation in the correct order. This exact interleaving process is what engineers mean when they say multiplexing. By mixing numbered frames in a single pipe, the protocol solves the queuing bottleneck that plagued older web traffic. Sharing a single pipe creates a new challenge. What happens if the server sends a massive file, but the client application is reading that data very slowly? To prevent a slow device from getting overwhelmed, HTTP/2 uses a strict budgeting system called flow control. As you see here, when the client's receive buffer fills up, it shoots a special frame back to the server called a window update. This tells the server exactly how many more bytes it is allowed to send. If the server uses up its entire budget before receiving another update, it pauses sending data for that specific stream. This protects the memory of the connection, so other, faster streams can keep flowing. Space in this shared pipe is valuable. Sending repetitive text headers, like long security tokens, over and over on every single request wastes a lot of bandwidth. To fix this, HTTP2 uses HPAC compression. Both client and server maintain a synchronized list called a dynamic table. When a massive 512-byte token is first sent, it's saved to both tables and assigned a tiny index number, like 62. On subsequent requests, the client only sends that 1-byte number. The server checks its table and expands the tiny number back into the full 512-byte string. These systems remove the overhead and keep the pipe flowing smoothly. But because both sides must maintain perfect, synchronized memory of those tables, the connection can break if the network hiccups even for a second. If a connection silently dies and reestablishes, the 2 HPAC tables fall out of sync. The client sends an index number the server no longer recognizes, triggering a compression error and causing your application to see intermittent failures. But the biggest vulnerability of sharing one pipe shows up when the network itself becomes unstable. Here, we see an HTTP2 connection on the left and standard HTTP1 connections on the right. Notice what happens when the network drops just one frame. This causes an issue known as TCP head-of-line blocking. Because HTTP2 runs on top of TCP, and TCP guarantees that data arrives in strict order, the operating system holds everything back until that single lost packet is retransmitted. Look at the left side. The entire pipe freezes. Meanwhile, on the right, the 5 connections that didn't lose a packet keep running perfectly. Because all of your streams share a single TCP connection, A tiny hiccup in the network stalls every single active request at the exact same time. This behavior dictates how you write your production code. If you are writing a backend service in Go, this code block shows the correct configuration. You should set your maximum connections per host to exactly 1. Opening a pool of 100 connections defeats the entire purpose of the single multiplexed pipe and wastes server memory for no reason. You have to monitor when a client cancels their request. If a user closes their app, the server needs to stop processing immediately. Otherwise, it burns processing power writing data to a stream that no longer exists. HTTP2 solved the problem of requests waiting in line, but it couldn't fix the way TCP handles lost data. To solve that, we had to move past TCP entirely. The next generation, HTTP 4.3, uses a new transport layer that allows each stream to handle its own lost packets, finally solving the problem HTTP2 couldn't touch.